So this video is going to be about the mirror equation and magnification equation. In our previous videos, we were able to talk about, okay, like with a concave mirror, if your object is in a particular location, your image would be in this location. It's either real or it's virtual or it's inverted or it's upright or it's minimized or whatever. And we can sort of talk about the relative size and characteristics of those images, but we didn't put any numbers with it. How far away is it? What exact size is it? And so we can find those things by using the mirror equation. So first, I want to talk briefly about some values here that we're going to use in our equations. And the first is to remind us of a value that we already have, which is the focal length, or f, right? The distance that the focal point is from the edge of the mirror along the principal axis. Another distance that we can describe is this distance is the distance of the object, or d sub o, right? This arrow here is representing our object. In a similar way, we can talk about the height of our object as h sub o. Now, in order to discuss this, I'm going to draw in our image in sort of a relative location. If I want to compare the height of my object and the distance of my object to my image, I need to have similar values for my image as well. So I can say, oh, this is the distance that my image is from the mirror, as well as the height of my image. And so using these, I can have two equations. And you can find videos of how these equations were derived, but for now we're just going to talk about what those equations are. And the first is the mirror equation, which is 1 over the focal length of the mirror is equal to 1 over the object distance plus 1 over the image distance. So that's one equation, which is great. We can also draw a relationship between the heights of our images and our objects. Right? This relates the relationship between the distance of the object and the image is related to the focal length of that mirror. And so we can also talk about the heights. And this is done through the magnification equation. And the magnification equation states that the magnification as a value, right, 2 times, 3 times, or whatever, that's a ratio, right, is equal to the ratio of the height of the image to the height of the object, which is also equal to the opposite of the relationship between the distance of the image and the distance of the object. So, how can we use these two equations? Well, let's do an example together. This is an example from physics classroom on their mirror equation page. So let's read. A 4 centimeter tall light bulb is placed a distance of 45.7 centimeters from a concave mirror having a focal length of 15.2 centimeters. Determine the image distance and image size. So let's write out what we know. We know that the height of our object is 4 centimeters. We know that the distance of our object is 45.7 centimeters, and our focal length is 15.2 centimeters. We don't know our image distance or our image height. What can we do? Well, we can use our mirror equation, 1 over f is equal to 1 over the object distance plus 1 over the image distance, and solve for image distance. So 1 over f is 1 over 15.2. 1 over the object distance is 1 over 45.7. And we don't know, sorry, that's the object distance, we don't know the image distance. Now, I would put this into my calculator, and I can round at each step, but you want to make sure that even though you might be rounding when you write it down, you are not rounding in your calculator. So you don't want to round until the end of any equation or any process in physics until the very end. So if I want to make sure that I do that, I can write this as such: 1 over 15.2 minus 1 over 45.7 is equal to 1 over di. That ends up being approximately 0.044 is equal to 1 over di, and di ends up being equal to 22.8 centimeters. That's our image distance from the mirror. Now if I want to do image size, I can use the magnification equation, right? Height of the image to height of the object is the opposite of image distance to object distance. And I have all but one of those values, right? Height of the image is over 4 for height of the object. Opposite, 22.8, which I just solved for, over 45.7. And then I can say, well, that means my image height is equal to 4 times negative 22.8 over 45.7. Put that into my calculator and I get an image height of negative 1.99 centimeters. Again, because all of my values at the beginning have 3 significant figures, I'm keeping 3 significant figures in both of my answers. Now, what do these mean? And let's think about this problem. I'm actually going to move maybe up here. All right, let's think about this problem. Does it turn out to be like what we expected from before? Well, this is a concave mirror. It says so. Right? And we have some focal point, which is 15.2 centimeters away from the mirror. That means that our center of curvature would be double that distance, 30.4. And if we look at our problem, look where the light bulb is. It's at 45.7. So it is back here. So this is an example of an object that is beyond C, and we know that objects beyond C end up having images that are between C and F that are inverted. And what answers did we get for our image? Well, our image distance is at 22.8. That happens to be in this region, right? In between, it's less than 30 but more than 15. Right, so our image height is here. And we did get a value that makes sense, 22.8. And what about our height? Our height is negative 1.99. What does it mean for it to be negative? Well, let's think about this, right? Here, our object height was 4, and this was negative 1.99. So certainly just taking the values of those, we have a smaller image than our object, which again makes sense from what we've experienced. And this negative, remember that in physics, in many cases, a negative or a positive value implies direction. And we can think of this principal axis very similar to an x-axis, right? Everything above it is positive, everything below it is negative. And so a positive value for our object height means that it is upright. A negative value for our image height means that it is inverted. And that is exactly what we find. So this makes total sense for us. And that is an example of the mirror equation.